Hello everyone, this is Rahul and my friend Fani. We are studying third year electrical engineering in IIT Tirupati. Today we are going to present you a research paper which was published in CVPR 2010, that is on aggregating local descriptors into a compact image representation.
In this presentation, we address the problem of image search on a very large scale where three constraints have to be considered jointly: the accuracy of the search, its efficiency, and the memory usage of the representation. We first propose a simple yet efficient way of aggregating local image descriptors into a vector of limited dimensions, which can be viewed as a simplification of the Fisher's kernel representation. We then show how to jointly optimize the dimension reduction and the indexing algorithm so that it best preserves the quality of video comparison. The search accuracy is comparable to the bag of features approach for an image representation that fits in 20 bytes. We then address the problem of searching the most similar images in very large database, suppose like 10 million images or more. We put an emphasis on the joint optimization of the three constraints: search accuracy, its efficiency, and the memory usage. In contrast, our approach obtains a significantly higher accuracy with the typically a 20 byte representation rather than using other approaches like using GIST global descriptors. This is obtained by following optimization: the representation, that is, how to aggregate local image descriptors into a vector representation, the dimensionality reduction of the vectors, the indexing algorithm.
So here we have a bag of features concept. The BOF representation groups local descriptors of image. It requires the definition of a codebook of K visual words, usually obtained by K-means clustering. The BOF representation is obtained as the histogram of the assignment of all image descriptors to visual words. Therefore, it produces a K-dimensional vector which is subsequently normalized. The BOF vector is normalized using Euclidean normalization. The vector components are then weighted by IDF, which is called inverse document frequency term. In the following, we perform L2 normalization of histograms and use the IDF calculation. So, for example, we have three images and they are broken into pixels. Those are called visual words. Here we have 6 visual words for each image, and the image is broken into pixels and they are divided into these bins as the histograms given below. So this is the concept of bag of features. And we have Fisher kernel. The Fisher kernel is a powerful tool to transform an incoming variable size set of independent samples into a fixed size vector representation, assuming that the samples follow a parametric generative model estimated on the training set. In comparison with the BOF representation, fewer visual words are required by the most sophisticated representation. And there's another method, that is VLAD, vector of locally aggregated descriptors. We propose a descriptor derived from the both BOF and Fisher kernel that aggregates SIFT, which is shift invariant Fourier feature transform descriptors, and produces a compact representation. It is termed VLAD. Experimental results demonstrate that VLAD significantly outperforms BOF for the same size of dataset. This is cheaper to compute and its dimensionality can be reduced to a few hundred components by principal component analysis (PCA) without noticeably impacting its accuracy. VLAD. We propose a vector representation of an image which aggregates descriptors based on a locality criterion in feature space. First, we learn a codebook which consists of K visual words with K means, each local descriptor X associated to its nearest visual word CI, that is nearest neighbor of X. The idea of VLAD descriptor is to accumulate for each visual word CI the differences, that is x minus Ci of the vectors x assigned to Ci. Assuming the local descriptor to be d-dimensional, the dimension d of our representation is k cross d. We represent the descriptor by vi comma j, where there are indices running from 1 to k and j 1 to d, respectively. Index the visual word and local descriptor component. Hence, a component of v is obtained as sum over all the image descriptors, as shown here. And then the descriptor x considered of its corresponding visual word Ca. The vector v is subsequently L2 normalized. Experimental results show that excellent results can be obtained even with a relatively small number of visual words k in the following image. Here we have image which is taken in two orientations. These are the images and corresponding VLAD descriptors for k equal to 16 centroids. Hence we get d equal to 16 cross 128. The components of the descriptor are represented like shift with negative components in red. That image depicts the VLAD representations associated with few images when aggregating 128 dimensional shift descriptors. The components of a descriptor here map to components of shift descriptors. Therefore, we adopt 4x4 spatial grid representation of oriented gradients for each VI. We have accumulated the descriptors in 16 of them. We can see for each orientation of image, we have 16 of them, one per visual word. In contrast to shift descriptors, a component may be positive or negative due to the difference in the equation, as we have seen in the earlier slide here, xj minus Cij. That may give negative component, which is represented in red color.
Now let's come into the next section, vectors to codes. This section addresses how to overcome the problem of coding an image. Like, let's take, given a d-dimensional input vector, we want to produce a code of b bits encoding the image representation such that the nearest neighbors of the query vector can be efficiently searched in a set of encoded database vectors. We can handle these problems in two steps: a projection that reduces the dimensionality of the vector, quantization used to index the resulting vector. Now, approximate nearest neighbors. So we know that one of the most popular technique is the Euclidean locality sensitivity hashing. However, this technique is memory consuming. It requires several hash tables and trees. Instead, we use a different technique called the asymmetric distance computation. It is, however, significantly outperformed in terms of trade-off between memory and accuracy. It offers a better accuracy, which only encodes the vectors of the database but not the query vector. So let's take a short view into the ADC approach. So here each vector VI will be in a quantized version. So finding the nearest neighbor of X simply consists in computing in as follows in the formula. And the quantizer is defined as a given function below. Then the square distances in the nearest neighbor equation is computed using the decomposition. So we use the quantization method is chosen because of the excellent performance, but also because it represents the indexation of vector approximation. A database vector VI can also be decomposed as the following formula, where Q of VI is the center associated with the VI and the error vector generated by the quantizer. Now, indexation aware dimensionality reduction. As we know, dimensionality reduction is an important step in approximation nearest neighbor search, as it impacts the subsequent indexation method. Principal component analysis is a standard tool for the dimensionality reduction which is popularly known as PCA. This dimensionality reduction can be interpreted in the initial space as the projection, that is, X is approximated as xp equal to x minus sigma of x. So for indexing purposes, the vector xp is subsequently encoded as q of xp. So at this point, we make two observations. Due to PCA, the variance of the different components of X dash is not balanced. Therefore, the ADC structure, which regularly subdivides the space, quantized the first principal components more closely in comparison with the last components that are selected. There is a trade-off on the number of dimensionality D dash to the retained by the PCA. If D dash is large, the projection error vector is of limited magnitude, but a large quantization error is introduced. On the opposite, keeping a small number of components leads to a high projection error and low quantization error. So, balancing the components variance. This issue was addressed by allocating different numbers of bits to the different components. The ADC method does not have this flexibility. Therefore, we address the problem by performing an orthogonal transformation after the PCA. In other terms, suppose given the dimension D dash and X a vector to the index, we want to find an orthogonal matrix Q such that the components of the transform vector have equal variances. It would be optimal to find the matrix Q, minimizing the expected quantization error introduced in the ADC method. However, this optimization problem is not traceable, as the objective function requires to learn the product quantizer of the ADC structure at each iteration. Finding the matrix Q satisfying the simplified balancing objective is done by choosing it in the form of householder matrix, that is Q equal to I minus 2V B transpose. So now let's come into the joint optimization of reduction. Let us now consider the second problem, that is optimizing the dimension D dash. The square Euclidean distance between the reproduction value and X is the sum of the errors, which both depend on the selected D dash. The mean square error E of D dash is empirically measured as learning vector set L. This gives us an objective criterion to optimize directly the dimensionality, which is obtained by finding on the learning set the value of D dash, minimizing this criterion. So as we see in the table, vectors k equal to 16, d equal to 2048 generated from SIFT descriptor, we obtain the following average projection, quantization, and total mean square error. It is important to compute the measures several times, as the ADC structure depends on the local optimum found by k mean and leads to variant quantization errors. And the highlighted one is the optimal measurement of D dash. So hereby we come to the remarks. The choice of D dash is constrained by the structure of ADC, which requires that D dash is a multiple of M. For instance, by keeping D dash equal 64 eigenvalues, the valued set of the values for M is the follows. The optimization is solely based on the mean squared error quantization criterion. For this reason, it is not clear how our framework could be extended to another indexation method, which does not provide an explicit approximation vector. We apply the projection Q cross M before the L2 normalization of the aggregated representation. This brings a marginal improvement in the terms of image search accuracy. As we see the figure, this is the impact of dimensionality reduction and indexation. The above figure illustrates how each of the operation impacts our representation. One can even see that the vector is only slightly altered even for a compact representation of B equal to 16 bytes.
Now, evaluation, datasets, and local descriptors. To extract local features, we have used the experimental setup and the feature extraction software available online. More precisely, the regions of interest are extracted using the Hayes-Affine invariant region detector and described by the SIFT descriptor. We have used an independent image set for all the learning stages. The evaluation is performed on three datasets. The INRIA holiday dataset. This dataset is a collection of 1491 holiday images. 500 of them are being used as queries. The accuracy is measured by the mean average precision, is shortly called as MAP. And the next one is the University of Kentucky benchmark, that is UKB. This set comprises images of 2550 objects, each of which is represented by 4 images. Most commonly used evaluation metric for this dataset counts the average number of relevant images, including the query itself, that are ranked in the first 4 positions when searching the 10,200 images. Now, these are image vector representations. The VLAD descriptor equals or outperforms the Fisher kernel on both holiday and UKB datasets and significantly outperforms BOF, which is bag of features. Higher dimensional representation, which usually provide better accuracy, suffer more from the dimensionality reduction. On average, VLAD outperforms the Fisher kernel representation. For only d' equal to 64 dimensions, VLAD attains an excellent accuracy of mean average precision of 0.494 on holiday dataset. Now, reduction and indexation. Here is the table of balancing the variances. This table is a comparison of different orthogonal transformation matrices with VLAD of k equal to 16, d' equal to 64, and ADC 16 cross 8. These measures are averaged over 10 runs on the holiday dataset. And the first one is PCA dimension reduction, PCA followed by orthogonal transformation optimizing the variance balancing criteria, PCA followed by a random orthogonal transformation. And here we have MAB of for each 0.445, 0.457, and 0.457. Now, choice of the projection subspace dimension. How do we choose the projection subspace dimension? The figure depicts, this figure depicts that search accuracy on holiday with respect to reduction to different dimension d' with ADC 16 cross 8. And the experiments are averaged over 5 learning runs. As you can see, the best choice of d' correspond to the one found by our optimization procedure. For instance, for VLAD with k equal to 16, that is, you can see in the graph that VLAD k equal to 16 is red color line graph. We obtain the same optimum, that is d' equal to 64. Now, comparison with the state of the art. We have the table of different methods and their bytes UKB, which is performed on UKB holiday datasets and holiday datasets. Above shown is the comparison of the state of the art on UKB and holidays. As said, that is mean average precision. D' equal to 64 for k equal to 16 and d' equal to 96 for k equal to 64. And this is an experimental result of number of bytes versus mean average precision for 8 different ADC parameters, that is 8 cross 8, 16 cross 8, and so. Above is the MAB for search on holidays dataset. For a given number of bytes, the optimal choice of d' is computed and only the results of the best codebook size, that is k equal to 16, 64 or 256 are reported. On large scale experiments, we have the following experimental graph result, that is database size versus mean average precision. This picture depicts the search accuracy as a function of database size. As we can see, for 10 million dataset search, the VLAD, the blue color line, that is VLAD k equal to 64, IVFADC 16 cross 8 is the best method for computing larger dataset. Timings for search results. That is, what is the timing elapsed for a search result? Timing experiments have been performed on a single processor core. Searching our 10 million dataset for VLAD vectors with k equal to 64, reduce it to d' equal to 64 dimensions takes 7.2 seconds when Euclidean distances are exhaustively computed. Now, searching with ADC 16 cross 8 takes 0.716 seconds. While using the IVFADC 16x8 variant takes 0.046 seconds. This timing is better for a significantly better accuracy. And here is the reference of the research paper. It's compiled in link. Thank you.